guys, welcome to Devil's Tower! Get excited! Okay, this is the first national monument of the United States, so pretty awesome to be here. Named by President Theodore Roosevelt on September 24th, 1906, and we are located in northeastern Wyoming in Crook County. I know it's going to be hard to pay attention to me and the prairie dogs, but
no, I just saw them all like cheer, so I was like, they all went like.
We are located on the northwestern edge of the Black Hills Uplift, and it is the most upstanding feature of the Great Plains. It raises 867 feet high, and it is a butte, literally and physically. Yeah. So it's igneous rock, and it is made of a specific, special kind of igneous rock that we'll get to in a little bit. It is a small national park. It's one of the smallest ones. It is 2.1 square miles, and the walk that we're probably going to do is the Towers Trail, which is 1.3 miles, just going around the base of it. So, but even though it is small, it is mighty and has a lot of unique significance, geologically speaking. And its most notable feature is its columnar jointing. So when we get up there, we'll be able to see. So you can see the pillars, but when we get up there, like actually close up, we should be able to see the hexagonal and pentagonal shapes. So 6-sided features, and those formed from the way it cooled underground. And so there are several theories of how Devil's Tower actually formed. Basically, what we know for certain, I believe, is that it's an igneous intrusion, which means it formed from lava underground, and it cooled slowly, compared to whether it was like a volcanic eruption. That would be lava, or I mean, magma is below ground, lava is above ground, so it cooled slowly versus on top. And we know that for sure because of the type of rock it is. So it has chunks or
porphyry.
Yeah, porphyritic components, which means there's just big visible chunks inside the aphanitic ground mass. And so one of the theories that geologists thought in the 1800s was that it was a stalk, which is basically like a small intrusive body formed by magma, which cooled underground and then was exposed due to erosion. 1907, people thought it was a laccolith, which is an eroded remnant of a volcanic...
Sorry.
You're good, you're good. So think of like a mushroom-shaped mass of igneous rocks that intrudes between layers of sedimentary rocks. Another idea that people thought was that it was a volcanic plug or a neck of an extinct volcano. However, the lack of volcanic debris, ash, anything around, leads them to believe that this was not true. In 2015, the geologist Zavada proposed a hypothesis that it was a Mar diatreme volcano, which has since probably been debunked, but that was when magma encounters groundwater underneath the ground, and the hot temperatures turn the water into steam, and this causes like an explosion. And then the Mar is the crater that forms, and then the diatreme is like the triangle kind of dome shape, or not dome shape, but triangle shape underneath the ground that magma would have been in and cooled, and then it would have been uplifted and exposed. And basically what we know for sure is that it is definitely igneous, and it's definitely formed around sedimentary rocks, and it cooled underneath the ground and then took 5 to 10 million years to become exposed at the surface. So now to the interesting part, it is made of a rare igneous rock called a phonolite porphyry. So phonolite determines its mineral composition, which is going to be like lots of silicon, aluminum, sodium, and then the porphyry is indicative of its texture, which is having the visible crystals of feldspar in the gray, small, fine-grained aphanitic matrix. And if you look around, especially when we were over at our camp, the thick red bottom portion was the spearfish, which was Triassic in age, so getting younger but still old, so 225 to 195 million years ago. On top of that, we've got a white, smaller column that we'll see, which is the Gypsum Springs Formation that formed in the middle Jurassic. And then we have the Sundance on top of that, which is made of 2 units, the Stockade Beaver Shale and the Hewlett Sandstone, and those were late Jurassic. Basically, the rocks around Devil's Tower eroded away, and Devil's Tower was able to be uplifted, and that's why it is such a prominent feature. I mean, look around, there's nothing like it anywhere in sight besides small mounds and whatnot. However, it is related to several features around the area, so if any of you are familiar with the Missouri Buttes or Crow Peak or anything like that, they kind of are related in the fact that they are composed of the same phonolite porphyry, which may be due to the way it was formed of it being an igneous intrusion. So think of like, there's 3 different kinds of intrusions. So there's sills, and there's dikes, and there's batholiths, and some geologists believe that it is a sill, which is basically a horizontal sheet of magma that formed between layers of sedimentary rock, and that's how we would be able to see, yeah, if I have a thing I could show, it's kind of like a dome or an egg shaped. So if you were to trace out those different structures, you would see they are all composed of the same composition of the phonolite porphyry. And just to talk a little bit more about the joints, so they formed from the cooling and contraction of the magma underneath the ground, and the stress points allows like for cracks to radiate out, which creates the unique feature. And this is, I think, like the best example around the world. It's not unique to just Devil's Tower, but it is like the most prominent and like largest example in the US at least. And if you saw when we were coming in, the Belle Fourche River, or that might have been a small tributary, but I think the sign said it was, which was way smaller than I thought it would be, but still mighty back in the day. And so that was part of the reason, not just wind and weathering and, you know, what have you. The erosion of the river caused erosion, which allowed more of this uplift and this amazing feature to occur. The phonolite porphyry, like I already said, it is made of a gray aphanitic ground mass, so think fine-grained, and then the feldspars, which I believe are sodium-rich orthoclase, are the large chunks that I'm not sure if we'll be able to see from that far away or not, probably not, but just a couple more notes about it. This place is super famous for its like indigenous or native tribes, so a lot of people back then, they thought it was like sacred. They would go there for gatherings and ceremonies, and they would hold their things that they would do like preaching, and they would talk about life and, you know, everything. But it was important to them because it was like, look around, like I said, it's super unique for its structure. But so there's been a bunch of stories about like what they think it is and how it formed, and that's a story for another day. But some people think it's a petrified tree, like the bark is the joints, and it's not at all. And then some other tribes think that it's the claws of a bear. So there's like the story that there's 7 girls and they were taking a hike, and then they saw a bear, or there's another story that a boy that was with them turned into a bear, and they climbed up on this rock and they said, please save me, and the tower grew and saved them. And I'm not sure if we'll see the stars tonight because of the fog and the haze, but apparently the girls died and they became stars. And so that's really interesting. I thought that, you know, like we think of it way differently than they think of it, and it's important in all aspects. Hot off the press, you are not allowed to climb on Devil's Tower right now because the peregrine falcons and the prairie falcons are nesting, they are migrating, and so they have it blocked off right now, which I thought was interesting. This was just on the news yesterday. And some people call it Bear Lodge, some people call it Devil's Tower, but all in all, it's really interesting, and they get up to 5,000 people that climb it every year, and we were just talking about it today when we were at Jewel Cave, and so it's got a lot of unique geological importance, and that's why we're here studying it. Thank you.
Cool. Did you read anything about the squirrels?
No.
So there's squirrels that live on top, and they're unique.
Okay.
Because they're isolated.
Do you know what they're called? Like, are they just called squirrels?
They did isolate
they're like a
themselves.
unique.
I'm curious. I would have like saw the name and then not put 2 and 2
How'd they
together.
get up there?
So, got me. I don't know. I think we might see some signage when we're in there, but there's some kind of squirrel that lives up at the top.
Okay.
You missed it. There was one of these guys stood up and went like, "Ah!" right in the middle of your
every
talk.
couple
So if you
minutes.
saw
Yeah, they were
people like
doing it.
laughing, that was it. It was pretty cool. Okay, so ignore this one. This is a laccolith. All right, so picture flat-lying sedimentary rocks being intruded from below. So you have what's called a feeder dike coming up from depth, carrying that material, and it hits a horizon that it can't punch through, and so it spreads out and it arcs those rocks up. So that's a laccolith. Now imagine a feature like this that is the difference between a sill and a laccolith is a sill is it comes up and it just like spreads out really wide. The laccolith actually has kind of a flattish bottom and then it bows it up on top, right? Kelsey mentioned that mushroom shape, okay? So think about that feeder dike. Instead of being like a pipe, think of it like a big long fracture. And instead of it coming up in one specific location, it comes up in several locations along that fracture. And that's why the idea of a diatreme or a volcanic neck has lost favor, because they've done geochemistry on Missouri Buttes and Crow Peak and a few other peaks in the northern Black Hills. So that's the Black Hills that we just came out of, and they all have very similar petrology, which Dr. Harris is going to talk a little bit about what a phonolite is.
It's really interesting. Has anybody heard of phonolite? It's weird. Okay. Are you done?
Yeah,
Okay. So, we'll do quick and dirty.
the red is really good.
Yeah, give me that one. Okay, we'll do it upside down. Is there anybody familiar with this? Q, A, P diagram for plutonic rocks, yeah? Quartz, alkali feldspar, plagioclase. What is like, this is gonna be kind of ugly. I don't know, like here. What's this? Quartz rich, alkali feldspar rich, some plagioclase.
Nice.
No, granite, yeah. Gneiss is metamorphic. This is for igneous plutonic rocks, or coarsely crystalline phaneritic rocks. Okay, what's over here? Now we're getting into the land of obscurity. If you don't know, if you start with a granite and you add more plagioclase, you get a granodiorite. Over here, you start getting some more obscure stuff. That's a tonalite, which is a rock that's only quartz and plagioclase, which is getting weird. If you know anything about Bowen's reaction series, you've got calcium-rich feldspar up here. Quartz is like way down there. So that's a weird rock right there, because it's got this stuff and that.
Right?
Right here?
No,
It's
I said
albite.
orthoclase.
Oh, yeah.
It's right there. So this
The other places
is
here, muscovites around
sodium.
here. Albite, anorthite, solid solution. Gradual change because they're homogeneous. Okay, and down there's quartz. Tonalite's weird because it's got this with that from the residuals here. So that's a weird rock. We're gonna get weirder though. So down here we've got more obscure stuff. You've got a syenite, you've got a monzonite, and then over here you've got your like mafic stuff. So all the mafic stuff, if you're only thinking about quartz, alkali feldspar, and plagioclase, you've got all your intermediate and mafic stuff down here, and the difference is the enrichment in calcium or sodium. Okay, so you've got diorites and gabbros right here. Now, this is where we get real fun. There's another land down here that gets an F for feldspathoids, and these are, just to paint broad strokes, foid-bearing variants of the stuff up here. So you have a foid-bearing monzonite and a foid-bearing monzocyanite and all kinds of goofy stuff down here. But the key is that these are feldspathoid bearing rocks, and they are not compatible with quartz bearing rocks because they're so silica depleted from the magma. So if you have so little silica that you can never make any quartz, you're down here in this lower ternary diagram where you're made of some amount of alkali feldspar, some amount of plagioclase feldspar, and some amount of a mineral series called the feldspathoids, which are kind of like silica depleted feldspars.
If you've seen blue sodalite in a crystal, like in a rock shop, sodalite, nepheline, are two common ones.
Okay, so you've got albite, NaAlSi3O8. Guess what? If you want to make a feldspathoid, just take a silica out of there. It's like that. It doesn't balance, but that's a very simplistic way of thinking about it. Okay, so those are the feldspathoids. There's not enough silica to ever make quartz. You get rocks down here that are super silica depleted. Where does phonolite show up? Keep in mind, this is phanerite, right? So you've got coarse crystals. Where would a rhyolite be on here? What's the aphanitic variant of granite? Rhyolite. So it occurs right here by chemistry. Okay, they're chemically the same. Like if you were to smash them up and send them through a mass spec, they would be indistinguishable. The difference is the crystal size. So by chemistry, rhyolites and granites are the same. Phonolites are like here. It's like a lot of alkali feldspar and a lot of feldspathoids. Now these aren't super useful for aphanitic rocks. We don't usually categorize aphanitic rocks on here, but it's a good way to place what type of rock the phonolite is. No quartz, because quartz is incompatible. If there was enough silica to eventually crystallize quartz, you wouldn't have feldspathoids, right? You have to be either in the top diagram or the bottom diagram, but not both. 99% of the time. There are rocks that have feldspathoids and quartz. There are always weird examples because Earth is weird, but as a general statement, we're down here. The other way, and the way we more typically classify volcanic rocks, is by chemistry. Why, as I draw this, would we more characteristically categorize volcanic rocks by chemistry as opposed to volume percents of different minerals?
Like temperature and pressure conditions?
No, think classification. How might we know where we are? Like, why would we know something's a granite on this diagram?
The
Crystal size.
You're very close.
No, the mineral characteristics. Like
It's
ones
the
that
modal.
occur to- yeah.
You would count the amount of quartz. You would count with a microscope
right.
the amount. You are right. You're all right in different ways. to name this rock, you would make a thin section. You would count how much quartz, count how much alkali feldspar, count how much plagioclase. Why can't we do that for a volcanic rock? It has minerals. They're really small.
Yeah.
You're in a microscope. You're like 100 magnification. You're like, I don't know what that is. It's way too small. So we categorize them by their chemistry, and you end up with the same stuff because thermodynamics helps us really well predict what you've got here. You could take a big vat of a specified amount of silica, aluminum, oxygen, whatever, and crystallize it by thermodynamics, and you'll get the same thing every time. So the rock right here we got cheap by cutting a thin section. For a volcanic rock, you have to send it off to a lab. But the chemistry of a granite is the same as the chemistry of a rhyolite. We just can't count the crystals in the volcanic rock. So instead, you look at the amount of sodium and K2O versus the amount of silica.
Those are called the alkalis. Potassium and sodium are the alkalis.
Yeah. So over here, we've got percent silica going this way. We've got amounts of the alkalis over here. This is called a TAS diagram. Total alkalis and silica. Na2O, K2O. Okay. Down here, we're depleted in the alkalis. This is the land of this side of the diagram, but for volcanic rocks. So what would be over here? Well, actually, it's this whole thing. What would be the highest silica percent for volcanic rocks?
100.
Well, what rock type?
Oh.
Silica enriched volcanic rock. Felsic.
That was it, yeah.
Yeah, is what rock?
Right.
Rhyolite.
Yeah.
Rhyolite's over here. And then we move this way, the whole way to basalt, which is over here. Picrobasalt's down there. Andesite's in the middle with some other stuff. Okay, but those are depleted in these. This is what's really interesting. Like a typical rhyolite's over here. Phonolite is like way up here. That's why it's right here, right? Because you've got alkali feldspars and feldspathoids. Those are enriched in sodium, they're enriched in potassium, they're enriched, and they're very depleted in silica. So right here, coarsely crystalline rock, finely crystalline version right here is strictly by chemistry. But super duper enriched in sodium and potassium, relatively depleted in silica. Trachyite is right here, you might have heard of. Trachyite would be like here as a volcanic variant. That's a lot to take in. But the reason why this is interesting is if you ask people to name a felsic rock, granite, rhyolite, because that's what most of it is, phonolite is really weird. It's a really weird rock. It's way outside of what types of rocks we generally find in most tectonic situations. So it's got a really unique chemistry, which is pretty fascinating. And it's porphyritic, which is even cooler. Yeah. Okay, what questions do you have about that? That was a lot to take in.
Not necessarily about that, but I have a question about the columnar.
Oh yeah.
Doesn't it usually require like relative cool area around the?
It's slow cooling.
Oh, it's slow cooling. I thought it was fast cooling.
Well, if it was
Kinda,
fast cooling,
yeah.
wouldn't it be above ground? Like, immediate?
No, lava flows cool with columnar jointing as
Oh,
well.
that's true. Yeah.
So it's the columns are representative of the cooling direction. So it cools from the ends to the middle. So if it's a lava flow, right, you have along the ground, this is what I was talking about before, along the ground, right, the lava's flowing along the ground, cooling along the ground. It's also got a contact, it's the lava air contact, it's cooling from the air, and so, but it cools in this direction, right, because the inside is insulated, so you can get columnar jointing. And what's happening is when you cool a total volume,
Let me get a wipe.
I have the wipes in here.
Yeah, I stuck them in your drink holder.
When you cool a total volume,
Oh,
God darn it, this is so good.
I know.
Um,
We actually talked about, I don't know who I was talking to about this volume.
Oh, surface area to volume.
No, it's the...
okay, let's do the equation. Okay. Mitch, what is that?
Rho.
Which is? Density, good. Yeah, density equals what? Yeah, mass over volume. Mass over volume.
The amount of mass occupying a space.
So if I start with a lava, I'm looking down on that lava, I have a volume of lava within this space with a mass inside. What can change? Let me ask it the other way. What
The
can't
density.
change?
Yeah, we're assuming like a closed system here.
The mass.
Why?
It's not gaining anything.
Mass cannot be created nor destroyed,
Yeah.
right? Just conservation of matter. So if I have the amount of mass in here, but what happens as it cools to the density?
Increase.
The density goes up. Okay, the mass can't change, so what has to happen to the volume? The volume has to decrease. So what happens? How do you decrease volume of rock in here?
You increase the pressure?
Nope.
You shrink it.
Yeah, you shrink it.
And what happens when it's shrinking?
It's cool.
Cracks.
It cracks. So now you have a coherent space. You're going to crack it, but you can't leave like big gaps. How do you do it?
Like,
Mud cracks.
Yeah. So those are hexagons. Hexagons are the closest thing to a circle in nature without
No, I'm doing this on purpose.
without leaving space.
I'm doing this on purpose.
It doesn't always. It doesn't.
They're not
so
perfect.
by
They're
law, right?
pentagons
They're
too.
not
Yeah.
perfect. Right? They're not perfect. So this is why you said pentagonal. But it's super cool because when you go up there, you're going to notice about 75% of the columns are hexagonal. About 15 to 20% are pentagons, and then the rest are kind of square-ish. But most of them are hexagons, and it's because of that. So what's happening is it's cooling like this from, in this case, top down, bottom up, in these columns. The columns are smaller at the top than they are at the bottom because from the bottom it's more insulated. From the top it's cooling faster. And the so it's cooling in this direction, so those columns are parallel to the cooling direction. Okay?
And that's why they're joints, because they're shrinking into these little central areas.
Yeah, and if you looked at it from the top,
tensional forces.
if you looked at it from the top, that's what it would look like. Looks like paving stones.
And no columns have ever fallen. So, no. Chunks of them have, but apparently
Oh,
no
like an
columns
entire
have.
coherent
Yeah, like an
one?
entire
yeah.
column is
I was
never
gonna say
like.
there's columns over
No,
the
they
trail.
break off all the time, and you're gonna see when we go up there. There's a bunch of boulders like all over the edge, with lichens on them.
Yeah.
Jake, lichens.
So, any questions on all that? Yeah.
If they're since they're cooling from the top and the bottom, are they bent because they're so hot and malleable, like in the center? Or
It's not going to be
just the direction
a
of the
uniform temperature. There's a lot of
That's this is one of the issues is when you get up there and you're going to see that at the bottom they kind of bow out. It could actually be that they were cooling and it was like pulsing, and so as more magma pulsed into it, it kind of
Oh, okay.
you see, or it could just be that it was cooling in that direction.
Right.
What do you guys think it is? Do you think it is?
I think it's a combination of both. I think it's a laccolith. I think it's a laccolith.
Okay.
Yeah. And Abby thinks it's a laccolith, and she
That's
lives
the
here.
most-
Yeah.
That's the most consistently
Yeah.
accepted idea.
Yeah. My friend Abigail Domagal is a professor at Black Hill State in Spearfish. She got her PhD in volcanology, and so she's been teaching geology out here for, actually, yeah, longer than I've been at Cal. Yeah, yeah. So, yeah, she knows what she's doing. That's what she thinks it is. So, all right, let's load up. It's super cool. So we'll go up there and check it out.